Hello, welcome to my YouTube channel. I am Dipchika Yadav and I am here to solve the problem of electrostatic, the force on electric dipole due to an infinite charged wire. So in this lecture we will take three cases for this question. In first case, the dipole is placed from the wire is in the direction of the wire. So the dipole, which is the combination of the negative charge and positive charge, equal and opposite charge, and the distance between the dipole is d. The dipole is far from the infinite wire. The wire is infinite, length of the wire is infinite here, and the charge, which is uniformly distributed along the length of the wire, and the line charge density of the wire is lambda. So this dipole is far from the wire with a distance r. So in this case, there will be no force acting on this dipole due to this line charge. Why? Because we know that the force acting on the negative charge due to this positively charged wire, it will be in this direction due to the attraction of the positive and negative charge. And on the positive charge, the force will be in this direction. And the magnitude of the force will be given by Q times of electric field. Q into E. So E is the electric field. E is the electric field due to this uniformly charged infinite wire, which is given by lambda by 2 pi epsilon naught r. Okay, so this electric field depends on the distance r. Lambda is charge density, which is constant charge per unit length, and the 2 pi epsilon naught is constant. So E is varying with the distance r and inversely proportional to the distance. So this r is same for the minus q charge and also same for the positive charge. R is same for both of the charges. So obviously the magnitude of the electric field will be same on minus q charge and plus q charge, but the direction will be opposite due to the nature of the charges. So on negative charge, it will be directed in this direction, and due to the positive charge, it will be directed in this direction. Okay, so here we can see that the net force is 0 because F is equal to Q times of E. So on positive charge, it is Q into lambda by 2 pi epsilon naught r. Place the value of electric field here in equation number 1. And on negative charge, it is Q negative due to the negative charge, lambda by 2 pi epsilon naught r. So then if we are going to add the vector sum of these two forces, then we will get 0. Okay, so there will be no force acting on this condition of the dipole. If the dipole is orientated in the direction of the infinite charged wire, there will be no force acting on this. Okay, so now take the case number 2. Now take the second case for this question, in which the orientation of the dipole is placed like this. This is infinite wire having the line charge density lambda, and the dipole plus q and minus q. The distance between the dipole is d, and half of the distance is d by 2 and d by 2. Okay, and from the center of the dipole, the distance from the wire is taken as r. So let's see what is the force acting on this condition of the dipole. Okay, so at the positive q charge, now the force due to this positive charge, again it is repulsion force, so it will be directed in this direction. and this is attraction force will be in this direction. Okay, and the magnitude of the electric field at here at the positive q charge and at the negative q charge will be different in previous case. Why? Because here the distance is vary. Distance is not same in due to the negative charge and due to the positive charge. So positive q charge is far from this wire with the distance r plus d by 2, right? It's r plus d by 2. Now, so what will be the electric field at positive q charge? It is lambda by 2 pi epsilon naught r. R is the distance from the charge and this wire, right? Distance between the charge and wire. So now the distance is sum of these two distances, r plus d by 2. So it's r plus d by 2, and obviously the direction will be in positive x-axis. So at negative q charge, the electric field will be lambda by 2 pi epsilon naught, and the distance is r minus d by 2, right? We need to subtract this distance d by 2 from the distance r. So it is r minus d by 2, and the direction will be negative x-axis. So now check the force F net. So F net is F on positive q plus F on negative q, right? Force F net will be sum of these two forces. So F on positive q will be equal to the it is E, and we need to multiply with the charge also to find the force. So FQ is Q times of EQ. So EQ is lambda by 2 pi epsilon naught r plus d by 2. Okay. So F on negative q will be equal to minus q times of lambda by 2 pi epsilon naught r minus d by 2. Okay. So here, if we are going to add these two forces, we will not get 0. Why? Because we can see that here the factor is not same. It's q by lambda by 2 pi epsilon naught r plus d by 2 and r minus d by 2. Okay. So here I am going to add these two values. So F net will be equal to q lambda. From the previous equation, q lambda by 2 pi epsilon naught r plus d by 2, right, and minus q lambda by 2 pi epsilon naught r minus d by 2. Okay. So if we take the common quantity q lambda by 2 pi epsilon naught, this is common, and it is 1 by, take the LCM, a plus b and a minus b, it becomes a square minus b square, right? And in numerator we will get, it's r minus d by 2 minus r plus d by 2. Clear? So if we are going to solve this factor, it's q lambda by 2 pi epsilon naught. In denominator it is this, numerator r minus d by 2 minus r, and after solving the bracket minus d by 2. Okay, so this r and this r is cancelled out, and this minus d by 2 and this minus d by 2 will become minus of d. Okay, so here the next step is, I'm going to solve the next step here. it become minus d by 2, and minus d by 2 is minus d, and q lambda by 2 pi epsilon naught, this is f net, r square minus d square by 4. So here the approximation, which is the distance between the dipole is the combination of equal and opposite charges. So the distance is very less than as compared to the distance r from the infinite wire, right? So this distance r, which is very greater than to distance d between the dipole, so we can neglect the d square as compared to r square, because if r is very greater than 2d, so obviously r square will be very greater than to d square also. So we can neglect d square is compared to the r square. So I'm going to neglect this value. So now f net becomes q lambda d by 2 pi epsilon naught r square. Clear? And the negative sign, which is showing that the net force will be in negative direction towards the wire. And now the term comes dipole moment, which is the strength of the any dipole, which is given by the charge and the distance between the dipole. This is the strength of the dipole, right? So we can replace this q and this d with dipole moment p, right? This is the magnitude of the dipole moment. So we can replace the q and d, product of the qd, with dipole moment. So it becomes lambda p by 2 pi epsilon naught r square. Clear? This is the F net force acting on the dipole in the second case. So this was the two cases of the dipole, the force acting on the electric dipole due to an infinite line charged wire. Now take the case third, in which the orientation of the dipole is just perpendicular to the wire thread of the infinitely line charged wire, just perpendicular to the wire. Okay, so I'm taking wire like this. This is point. It means it is perpendicular to the plane of this board, right? It is perpendicular to the plane of this board. Or we can say that if this is x direction, this is y direction. So the direction of the wire is just perpendicular or minus of z direction, right? So this is directed inward. Okay, so the dipole is now minus q and plus q here, and obviously the distance between the dipole is d. The orientation of the dipole is in the plane of this board, and the orientation of this wire is just perpendicular to the plane of this board. Okay, so these two are perpendicular to each other. Now check what is the force acting on this condition of the dipole. So here we can see that it is positively charged wire, right? Charge is uniformly distributed along the wire, length of the wire. So due to the positively charged and negatively charged, the electric field, the direction of the force on this negative charge will be directed in this direction, right? Attraction. And due to the positive charge and positively charged infinite wire will be directed in this direction. Clear? So here the direction of force making an angle theta with the horizontal. This is the angle theta. And here also this charge is also making an angle theta with the horizontal. Both of the cases we are here the angle theta is making. So check the component, right? So this is the direction of the force and this is the direction of the force. So now here we will get F cos theta, because in the direction of theta we will get the component of the F cos theta, and here the perpendicular component F sine theta, right? This is the horizontal component in the direction of theta, and where the angle is 90 minus theta, we will be having the component of f cos theta, right? So here in the direction of by making an angle theta here, so here we are having the two component. One is f cos theta directed in this direction, and this is the f sin theta in downward direction, right? These two are component of the forces now. Now we can see that this f cos theta and this f cos theta will be totally cancelled out. Why? Because both of the forces are same in magnitude but different in direction. This will be directed in positive direction, and here the direction of this force is negative direction. So both of the forces are equal in opposite. So these two forces will cancel out. Now the net force is due to the combination of these two components only, right? So F net will be equal to here 2F sin theta, okay, or that the direction is negative direction, so it's minus 2F sin theta. Clear? So let's check. If we take the magnitude, we will take the positive sign. So F net will be equal to twice of F sin theta. Now what is the value of theta and F? Okay, so F is here. F is Q times of lambda. So Q times of F on positive Q. So it's Q time of lambda. So it's lambda, electric field is lambda by 2 pi epsilon naught r. R is the distance from the wire and dipole. So wire and the charges, sorry. So here the distance. So if the distance, this is x from the dipole, and this is half of the distance d by 2, and this is also half, then obviously this is the hypotenuse, which is x square plus d square by 4, right? So here the distance between the charge and the wire is this one, hypotenuse. So here x square plus d square by 4. This is the force acting on the positive Q charge, and for the negative Q charge it is minus Q lambda by 2 pi epsilon naught. Again the hypotenuse is same. Here the same triangle, here the angle is also theta and theta, because this is the same. If the theta is here and theta is interior angle, theta is there. So x square plus d square by 4. Okay, now again put the value of f. We can see that the if we take the magnitude of these two forces, we are having the same value, q lambda by 2 pi epsilon naught root over x square by d square by 4. So if we take the magnitude, we are having same values. Okay, so it's 2. I'm going to rub the diagram. So F net will be equal to here twice of F. F is this. I'm taking magnitude only. So it's Q lambda by 2 pi epsilon naught x square plus d square by 4. Sin theta. So now what is sin theta? So our triangle was like this. This is d by 2. And here the charge minus q, and here the line charged wire, infinite line charged wire, and this distance is taken x, and this was the hypotenuse, which is x square plus d square by 4, right, in the last diagram, and here the theta. So obviously sin theta will be equal to just perpendicular by base. So here it is perpendicular and it is perpendicular by hypotenuse. So it is perpendicular and hypotenuse. So it's d by 2 by root over x square plus d square by 4. So this is the sin theta. Okay, so put the value of sin theta here. So now the force is 2q lambda by 2 pi epsilon naught root over x square plus d square by 4. Sin theta is now this. Okay, so it's d by 2. By 2 is here. Okay, and root over x square plus d square by 4. This square root and this square root becomes 1 power. So this 2 and this 2 will be cancelled out, and it is q lambda d by 2 pi epsilon naught root in root become x square plus d square by 4. Okay, single power. Now again the approximation, the distance between the dipole is very less than to the distance between the charges in wire. And q and lambda, product of the q lambda is dipole moment, strength of the dipole, so it is P, right? I'm going to replace key product of the q and lambda is P. So F net is now is lambda P by 2 pi epsilon naught, and neglect the d square by 4 as compared to x square. Why? Because d is very less than to the distance between the dipole and the wire, which is x, right? So d square by 4 is very less than 2x. So it is x square only. Okay. So now this was the complete explanation of the force acting on the dipole due to the infinite charged wire. In this lecture, case 1 and case 2 and case 3, we solved the 3 types of the cases. Okay, so if you like this lecture, then don't forget to like my channel and subscribe my channel. Thank you so much.